Okay. Okay, great. Greetings, everybody. Welcome to the second OSMU lecture for this year to be given by Stacy McGaugh. He is professor in the Department of Astronomy at Case Western University in Cleveland, Ohio. His fields of specialty include low surface brightness galaxies, galaxy formation and evolution, tests of dark matter and alternative hypotheses including MOND, and measurements of cosmological parameters. Stacy was an undergraduate student at MIT, a graduate student at Princeton and the University of Michigan, later held postdoctoral appointments at Cambridge University, Carnegie Institute of Washington, and Rutgers University before joining the faculty of University of Maryland in 1998, and in 2012 he moved to Case Western. Stacy is known in the field of extragalactic astronomy for his early work on low surface brightness galaxies and the elemental abundances in H2 regions. He has also contributed to the study of the kinematics of galaxies, being among the first to point out that low surface brightness galaxies are dark matter dominated and that they pose the cuspy halo problem. He also coined the expression baryonic Tully-Fisher relation. He predicted the first to second peak amplitude ratio of the acoustic power spectrum of the CMB. Stacy found surprising support for MOND in his work on low surface brightness galaxies. This has proven to be very controversial from the lambda CDM point of view, since it implies the non-existence of non-baryonic dark matter central to the standard model. Nevertheless, his predictions for the mass distribution of the Milky Way and the velocity dispersion of dwarf spheroids of the Andromeda galaxy have largely been confirmed by subsequent observations. Over to you, Stacy. Pleasure to have you with us today.
Well, thank you so much for having me and for the indulgent introduction. I feel like this is some guy I should meet. Sounds really smart. Um, so I want to tell you about predictions and observations of high redshift galaxies, hence the title. Obviously, there's been a lot of interest in findings of JWST over the past few years, in which essentially galaxies at high redshift are much brighter than they were expected to be. But first, I want to give you some context for how I came to this, and where the field is at. So first, this is how we got our current lambda CDM model. There are lots of, this is historical at this point, but the thing that really convinced me that lambda CDM was a leading candidate in the mid-90s was this Nature paper by Ostreicher and Steinhardt in 1995, where they showed from all sorts of different kinds of astronomical observations, large-scale structure allowed this kind of band in the mass density Hubble parameter plane, galaxy clusters combined with BBNs at this, direct measurements of H naught and omega matter, basically narrowed it down to this gray region. And you could have either an open cosmology that was allowed at the time, or a flat one with lambda CDM, and they made a perfect persuasive case in favor of lambda CDM, which led us to this now common figure of 3 or 4 parts dark matter, dark energy to 1 part dark matter with just a froth of baryons. And I wanted to mention this because this was cemented in a lot of our minds before the supernova observations of 1998. And in fact, I would have claimed to predicted that because in response to this, I actually wrote a little note that said, geez, if it's true that there's lambda here, then not only is, all these other things satisfied, but it predicts that the expansion rate is accelerating. And I didn't mean that as a prediction so much as how crazy would that be? Because at the time I thought an open universe was a more palatable alternative. But as we know, the supernova found accelerated expansion, and then the microwave background acoustic power spectra gave you uh, detailed constraints. And it's interesting to see. I really like predictions. One of the models that they advocated was basically very close to what standard lambda CDM is now. So that was 30 years ago. The thing that was standard up until then was standard cold dark matter, this point way up high, and that was clearly excluded. And so a lot of the 90s we spent just wrapping our head around how that could be, how we could exclude that. And Lambda fixed everything, or so we thought at the time. So this is an updated version of that same diagram. I've now zoomed in a lot because the data are better, but I basically wanted to reproduce the same sets of constraints. So these are modern versions of these constraints. And the points are the CMB fits labeled by their date. So the W map and then Planck results. That green band is basically the trench of chi-squared for such fits. Everything out of that green line is strongly excluded. And you can see how the CMB has sort of marched to lower Hubble constant and higher mass density as higher multiples have been incorporated into the fits. And it is the CMB fits that have walked away from the concordance region. All of the astronomical data still point to the same region. And of course, it was the agreement of the early WMAP results with all that that really cemented lambda CDM in our mind as it had to be that way. So there is this tension with Hubble constant, and that's the strongest tension, but it's not the only tension. There's also a tension with lithium abundance and BBN, and I could go on at great length about that, so I will refrain. I often hear cosmologists assert something to the effect that lambda CDM works so well, it must be right. And I have some sympathy for that attitude, but we've had to invoke these auxiliary hypotheses of the dark matter and the dark energy. And I'm not going to go into the dark energy any further, just concentrate on the issues concerning the dark matter. And note that lambda CDM works if and only if this stuff actually exists. That is, we need some entirely novel form of mass that is outside of the standard model of particle physics. And of course, we had a very strong candidate particle for that, the WIMP, the weakly interacting massive particles. This was a hypothesis that launched 1,000 experiments, and those experiments have succeeded in failing. That is, the experimentalists have done their job. They have searched the parameter space that you're now looking at, and they haven't found anything. And so down to some deep limit there. And that basically excludes everything. There are lots of predictions. I picked this one out for reasons you can ask me about later if you're curious. There's a cute anecdote about that. But basically, you know, this entire region was where WIMPs were predicted to exist circa 2008, and that's entirely excluded by experiment now. These folks I've highlighted up here, Waradwaj et al., have further pointed out that, you know, if you had WIMPs in these other regions, they would have an impact with the Higgs if they exchange anything at all with them, which is sort of the point of having a weakly interacting massive particle. And so basically almost all of this space is excluded, except for this tiny, tiny region right here. So now you can, of course, make up a particle that doesn't interact at all, and I call that an angel particle because sure, you can just make that up. But the original WIMP hypothesis is really not in good shape. Now, I have worked a lot on galaxies lately, and they're pretty things. So this is the poster child, just a nice image I was able to obtain at one point. And those who can speed read at the bottom, I've paraphrased Tolkien because my concern is that there's not just the vastness of the universe to explain, but the minute precision with which galaxies work. And that is not something that is natural to the dark matter paradigm. Okay, so just some basic facts. Of course, famously, rotation curves are flat. This is the mass model of this very same galaxy. On the right, you see a picture that includes both the stars in the yellow and the gas in the blue. And the gas is much more extended, so you can see in the rotation curve that allows us to trace the rotation speed much further out, and you get an approximately flat rotation curve, which is what we see all the time. Now you can take the observed mass distribution, the stars and the gas that you see, you can feed that to some kind of Poisson solver and work out what the rotation curve should be for what you see. And that's what you see in the red line there. That's what all the normal matter gives you for this case. And that does a pretty good explanation of the inside. You don't need any dark matter at small radii. But inevitably, you get to some larger radius where you do, where the red line falls short of the observed rotation. And so you need something extra. And of course, that's where the inference of dark matter comes from in this context. There's a lot more to it than that. When we built the cold dark matter paradigm, we knew there were mass discrepancies in galaxies like I just described, so we needed something else. We also, of course, knew from cosmology that you needed to grow structure by a factor of roughly 100,000. We didn't know the exact number even yet. We just knew that it was more than we could do with the baryons alone. And so that all wrapped up into the building the paradigm that we have now. There is more information that has come out in the data that did not inform that hypothesis building, and rather than corroborating it, tends to challenge it. So there are a number of scaling relations that have been well established empirically. One is just that rotation curves are flat. The other is this baryonic Tully-Fisher relation, and then finally the radial acceleration relation, which really encompasses all the other aspects of it. But you can see just by eye, looking at the rotation curves, these are rotation curves color-coded by the surface brightness of the stars. The high surface brightness galaxies are in red, and they have very steeply rising rotation curves that flatten out promptly. And as you go to lower and lower surface brightness galaxies, that was my original interest in this, is you find that the rotation curves rise more and more gradually and flatten out slowly. And, you know, that makes sense that there's fewer baryons in the center, and so they produce less rotation speed. That much made sense. But the amplitude of Tully-Fisher did not. This predicted that things should fall off of Tully-Fisher, and they don't. So that's the next piece, is that it's not just that rotation curves are flat, but that the amplitude of that flat rotation speed correlates with the mass of the stuff you can see, just the stars and the gas. Nothing about the dark matter. We've always assumed that the flat velocity was telling us about the dark matter, and maybe it is, but there's nothing in this diagram that has anything to do with dark matter. This is just observed. So this is on the left, the stellar mass Tully-Fisher relation. This is close to what most people mean when they say Tully-Fisher. Tully-Fisher was originally recognized as a relation between the luminosity and the line width, which were proxies for stellar mass and for the flat rotation speed. So that's what's on the left. And the dark blue points are, each one of those points is a galaxy. The dark blue points are star-dominated galaxies. The light blue points are gas-dominated galaxies. So there's actually more of that extended atomic gas than there are stars there. And so you can see in the left plot that those things don't fall on quite the same relation, and you get a lot of scatter. And that's because we have omitted an important mass component in the budget. We can fix that by adding the stars and the gas together. That's what you see on the right, and what I call the baryonic Tully-Fisher relation. And whatever physics is driving this gives you a nice relation that doesn't care about whether it's gas or stars. It also doesn't care if dark matter is giving you V flat. It's just what we observe. This is an important enough relation to worth noting that there is a simple equation. That line is the sum of stars and gas mass equals some constant times the flat velocity to the fourth power. And I give an estimate of that constant. It's been bouncing around between 45 and 50 as you expect as we improve. The observations, my current student, Francis Dewey, will have a new calibration of this very soon. But so that is a strong relation. I don't know what each of your backgrounds is. If you work in some high precision field, this may look like a lot of scatter. It is not. For an extragalactic relation, this is mind-blowingly, incredibly, jarringly tight relation. And in fact, if you go through the error budget, it's basically the scatter you see is just the scatter you expect from the uncertainties. It's consistent with basically a perfect power law. That is crazy. But you can see by eye again, looking at the rotation curves, that there's more to it than just that outer flat velocity. There is a correlation of the shape of the rotation curve with the surface brightness, that is the distribution of the baryons. And that seems to be dictated by the acceleration. So on the right is the same data, but replotted with the centripetal acceleration, v squared over r. And you can see again that the data segregate by surface brightness. And Milgram's A naught is noted on there. So the inner regions of high surface brightness galaxies are just in the Newtonian regime. That's where you don't need dark matter. And then as you get further out, the accelerations drop below that scale. That's where you do infer dark matter. And then for the bluest point galaxies there, the low surface brightness things, they're entirely in this low acceleration regime. And that is why I inferred that they were dark matter dominated. And that's why Milgram would say that they would be inferred to be that way. So here are some individual rotation curves. With mass models, the data points are the observed velocities. The blue lines are the sum of stars and gas. So what Newton predicts in the absence of any funny business like dark matter or MOND. And they're all different. There's a huge diversity in the shapes of rotation curves. But when you plot them in terms of acceleration, and that's what the lower panels are, there's the observed acceleration, v squared over r, against what Newton would predict for what you see. So it's basically the ratio of the black points to the blue lines there. And when you do that, you find that the data all start to lie on top of each other in spite of all the different details in the shape of the rotation curve. So this is what I call the radial acceleration relation. If you basically stack up all the data that we have, then they basically fall right on top of each other. You cannot distinguish individual galaxies in this plane. And you can fit a function, that's one that works. There are others. But the point is that there is a function so that if you measure the distribution of light, you can use that to construct the G bar there. That is the centripetal acceleration that is predicted by the observed mass in stars and gas. And then that is predictive of the total acceleration. Right? So you can just look at a galaxy and say how much dark matter it's going to have. Right? The dark matter is the excess over the dotted line there. And that's very systematic. It always follows this trend. Recently, we've been able to expand this to very low accelerations using gravitational lensing in a statistical sense. And so this goes down to incredibly low accelerations now. Current postdoc Tobias Mishtela has a couple of papers on it this past year. One showing that the rotation curves that you infer from lensing remain flat out as far as like a megaparsec, which is amazing. Getting out tens of kiloparsecs with the gas was already a long ways out. Now the lensing data extend that hundreds of kiloparsecs, and give a whole talk about that. The point is that there is just a single relation here. You only see a departure from Newtonian dynamics at these low accelerations. Um, that is all empirical statement. I'm not using Mond at any point here. I can fit that line and just say, okay, that's a good fit. But that happens to be the line of Mond. If Mond did not already exist, you would need to invent it to explain these data. But nobody wants to accept that right off. So the things that you do need to explain empirically is not just that rotation curves are flat, but that flat amplitude of the flat rotation speed correlates with the mass that you can see. That's the baryonic-Tully-Fish relation. And then it's point-by-point agreement between the predicted acceleration from the observed baryon distribution and what's observed in the radial acceleration relation. And there are some ancillary results, something I call the central density relation and Rinzau's rule, which I won't go into for time. But basically, the effective force law in galaxies is that blue line, and that happens to be Mond. But that blue line is established by the data now without reference to Mond. Just Mond happened to already exist, so we were honest and said, geez, we didn't discover this. Milgram actually predicted it 40 years ago. And what attracted my attention to this was that, I'd studied these low surface brightness galaxies. I had my own prediction for what they would do, and I expected them to shift off of Tully-Fisher, and they did not. And it turned out that the only theory that predicted correctly that they would not was Milgram's Mond. And in fact, he said so right in his original paper, that this galaxies with low surface brightness provide particularly strong tests. And that is because they have these low surface densities, means low accelerations, right? The baryon distribution gets you into the Mond regime, as you could see empirically by eye, just when I plotted the accelerations in the color-coded panel. And so, when I first read that, I was like, no way. I literally, my first thought was, great, I now have the data to falsify this stupid theory. I actually had a lot of respect that he was making predictions for low surface brightness galaxies a decade before I had studied them because, at the time he wrote, a lot of people argued they didn't even exist. And much of the arguments I had with people at that time were just say, yeah, well, here's one. There are lots of them, they do exist. And he was not just, saying if they exist, but here is what they will do. And the bullet points there list all of the things, what they would do. And much to my surprise, you could just go down the list and it's like, check, 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 check. All of those predictions came true. So I've been testing the theory ever since, and it comes out surprisingly well, with some glaring exceptions. Um, I'm going to skip most of that until the most recent test, which has to do with these high redshift galaxies. And so it's important to understand what each paradigm predicts. So on the left here is the standard growth of structure in the cold dark matter paradigm. You have the linear growth of perturbations. It comes out of perturbation theory from general relativity. Nice elegant solution that gives you this linear growth. So the dark matter can start forming the skeleton of cosmic structure before the baryons are released from the bondage of the photons. Then they can fall into that existing structure. And that gives you a growth rate, and that is very well matched to both the CMB and the current amount of structure, if all the parameters are just right. And bear in mind the age redshift relation. We get obsessed with the highest redshifts for good reason, but half of the age of the universe is before redshift 1. Redshift 3 gets us back to the first couple gigayears after the Big Bang, and things pile up closer and closer. So redshift 9, 10, that's in the first half billion years or so. But that's all very early. Z of 9 is not all that much earlier than Z of 3, depending on how you look at it. Okay, so this is the prediction of a simulation, specifically the TNG 50 simulation of the illustrious fleets, but all lambda CDM simulations do something similar to this, because this is showing you the fundamental prediction of the paradigm of hierarchical growth. So there are four different galaxy-like objects that have been selected for the simulation to have a particular stellar mass by redshift 0. That is characteristic of the mass of elliptical galaxies nearby. Um, and you can see everything starts out small at high redshift. You have lots and lots of little chunks, and those assemble hierarchically, merging into larger and larger things. So on the left is the largest progenitor object. That is what you would call the galaxy if you could look back at it through time, and all these other things are merging into it. The top two panels still have star formation going on at the present time, so that would be a late type galaxy like Andromeda or the Milky Way. The bottom panels are red and dead. They stopped forming stars a long time ago. Those would be elliptical galaxies. But even in those cases, they're still forming stars at redshift 1. They're still exploring ongoing mergers. And in all cases, in those first 2 gigayears, that is redshift 3 and greater, their progenitors are tiny. Okay, that is the prediction, and that is why everybody has been so surprised by JWST seeing such bright galaxies at redshift 10. That's not supposed to happen. Here's another visualization of it from Young et al. This is cutting back in a look-back cone in a simulation. The size and color of the points coded by the stellar mass. And so you can see below redshift 1, you get some of these 10 to the 11 solar mass galaxies like we were just looking at. But those become increasingly rare as you go to higher redshift, and they're just basically not there above redshift 4. And even above redshift 6, now you're down to pretty small masses. So again, that's what lambda CDM predicts. And it's a fundamental prediction because this hierarchical assembly is what the mass is doing, what we can simulate well with the dark matter. And how we relate that depends on how we paint the light on that, how things form stars. But that's a detail compared to the structure of assembly. So that's the linear growth that we expect with cold dark matter. In MOND, turns out that MOND is a nonlinear theory. And so as soon as the photons let go of the baryons, they basically, it's like pulling the rug out from under them. They're like, oh, I'm in the low acceleration regime. And they behave like they have a lot of dark matter. And the growth of structure proceeds very rapidly. Now, fundamentally, MOND is just a boost to Newton. So the same things happen. You get the emergence of a cosmic web. You see the same kind of structures emerge. It just happens earlier in MOND, happens faster. So if you want to think about galaxy formation in MOND, now you have to go way back and just think, okay, there's some background that is expanding, and we can hope that it's something like our standard cosmology, and Bob Sanders made a convincing argument that it could be, doesn't have to be, but we'll just assume that we have MOND going on in some expanding background, and then you ask, well, what are the dynamics of a sphere that decouples from that general expansion and recollapses? And of course, you know the solution in the standard cosmology, if you have an overdensity that has omega matter greater than 1 just in that top hat, then you can solve the equations and ask when it recollapses. And of course, conventionally, it takes forever because the initial overdensities are tiny. So that doesn't form a galaxy. But you do that exercise in MOND and you find, oh, it's actually, this happens pretty fast. And so Bob Sanders did this, and this is basically the cycloidal curve that such a Mondian sphere experiences, specifically a 10 to the 11 solar mass sphere operating under MOND. It decouples from the background expansion, reaches a maximum expansion after 300 million years, and recollapses in a comparable time. So you're going to form a massive galaxy in about 500,000,000 years. And Bob Sanders explicitly said this way back in 1998, right? Remember the previous century? Um, this is a quote from that paper right in the abstract. Objects of galaxy mass are the first visualized objects to form by z equals 10, and larger structure develops rapidly. Um, for reference, the contemporaneous prediction from lambda CDM was that present-day galaxies were assembled recently at redshift less than 1. And you can see why that is from the merger trees that I showed you. So that's a pretty stark difference in predictions. Now, it's a bit more complicated than that because, of course, different shells expand and contract, and you don't always have the same center of things. So it should be a big mess that basically, I imagine, does something like Lynden-Bell's violent relaxation. It's also going to be an inefficient process. You need a Mondian subregion that behaves in this fashion. And of course, there's all sorts of stuff going on. So some regions will succeed in doing this, but not every place will do this all the time. And then this is now a logarithmic scale, so the collapsing side gets way compressed, but basically you see the same kind of feature over and over again. As a function of mass, the time scale is really compressed, so globular clusters form very promptly. So they're the oldest things around. Um, Galaxies form in the first, 500,000,000 years. You already start getting galaxy clusters after a couple of giga years, so redshift 2, 3, something like that. Um, and so, that's just what we expect in MON, that very rapid nonlinear growth. This is a crude picture just showing that you get the same kind of structure, so lambda CDM on top, MOND at the bottom, starting from the same initial conditions. You see the same structures emerge, but note the redshift. It happens much quicker in MOND. And the empty regions get clear in MOND, so that the fact that the voids are swept clean by redshift 0 in MOND is another prediction. The movie looks the same, it just runs faster. Now, I'm going to talk a bit about some work Jay Frank did as a grad student almost a decade ago now. And Jay was interested in identifying structures at high redshift. He was looking for proto-cluster candidates. And this is an example at redshift 3, where you can see galaxies are clumped together in position on the sky. Some have the same redshift, those black points within that. Right, so this is number as a function of redshift. This is position on the sky. So everything within that redshift band is a black point there. And yeah, it looks like a cluster. And these are actually not hard to find. There is sometimes a lot of surrounding structure. Sometimes they're just all by themselves. You get this spike in redshift space. And so he identified a lot of protocluster candidates in this fashion from redshift 2 to 6. And those galaxies, there are a lot of galaxies in those things. So he could fit luminosity functions to those things. So these are luminosity function fits. And I show you this just to motivate this apparent magnitude. This is the characteristic luminosity of, again, the Ni and the Schechter function in each of these different redshifts for all these galaxies. And there are many dozens, even hundreds of galaxies in each of these fits. So we know the apparent magnitude of the characteristic Schechter luminosity very well. It's not just an anecdotal galaxy. It is characteristic of the population at those redshifts. And then that's what this looks like. So this is the apparent magnitude. Bright things here, faint things there. As a function of redshift, the blue points at the highest redshift are from Jay's work. Other people have been doing that, so they're shown as black and darker blue points. And the orange line is the prediction of the Millennium simulation. And Jay went into a look-back cone of the simulation applied the same algorithm that he had used on the data to find structures in the simulation, and that's what the open boxes are. So that was the prediction. If the universe looked like that, that's what we would have seen. Instead, the data follow the path of evolution of just a generic monolithic object that followed an exponential star formation history. This is, if you're not familiar with this sort of thing, it's just a boilerplate standard model for an elliptical galaxy. And it was the very first model that I had Jay construct because it's like, okay, make sure you can do this thing. He built other models. I haven't shown them here because none of them work. That boilerplate thing worked better than anything else. Now, taking those same data and translating them into stellar mass and cosmic time, you get this relation. Again, the same exponential star formation model. A lot more scatter at high redshift because you expect that as you get to early times, the stellar populations flicker on and off more. But then those settle down and just stay at a constant mass around this 10 to the 11. And that was established back at redshift 2, right, a long time ago. The prediction from the simulations come nowhere near to that. So that's the Illustris simulation. The green line there is the fire simulation. They form stars more prolifically, but they still have the same hierarchical assembly. And so there's nothing big at high redshift. That is the prediction of lambda CDM. So here it is again. And now I've just shown one of these merger trees, but I've also shown its stellar mass growth. So that's what the red line is, how the stellar mass of this largest progenitor assembles as a function of redshift. It's growing up along that jagged line. And then you can ask, okay, what's the median for Illustris? It's that dashed line. And what's the variance? That's that band. And the data that I just show you follow this monolithic line. There is a huge difference already at redshift 3. You don't have to go to redshift 10 to see that this is an issue. It gets worse, but it's an issue there. There is more mass in place in individual galaxies already at redshift 6, 10 than should be possible in lambda CDM. And of course, that's what we built JWST to do. This is just for those who don't follow the technical details, I want to give a quick review of how that works. Right, so this is launched into deep space. It has a sun shield, so it keeps this side to the sun. It gets actually hot on that side. So you have a series of shields that take advantage of the vacuum of space so that it gets very cold on the operating side so you can work comfortably in the infrared part of the spectrum. And so here you can see the temperatures coming up when they switched on the active cooling for the instruments, liquid helium cooling, so that sets a finite lifetime for the thing. But it stays hot on the sunlit side. It gets very cold on the other side. It's really a triumph of engineering. Here is the wavelength sensitivity of the onboard instruments. In IRCam is what you mostly see images from. Here are the wavelengths at which it operates. The traditional optical V band is what our eyes see basically. Gets redshifted out to here at redshift 2, out to here at redshift 5. That's all comfortably within in IRCam. And that's what JWST was built to do, to take pictures of galaxies at high redshift that we could see what was going on the same way our eyes would see it locally. We didn't really anticipate, well, Bob did, but most of us did not anticipate things at Z of 10. And so it gets harder to work at those higher redshifts. But JWST was basically built to see this era of galaxy assembly, and it does. It's really amazingly successful. These are two images from the Spitzer, sort of a predecessor NASA infrared mission, which was a great mission. I used that a lot, and you can see how much better the image quality is in JWST. And here is a deep field from JWST, and most of the things that you see there are distant galaxies. Lots and lots and lots of them out there, including things like this GNZ11, which is way down there. Well, Z11, that's kind of suggestive, isn't it? But there are lots of other interesting things, and you can go, it's really interesting just to go through the data and look at what's there. It's a big universe, lots of stuff going on. Including, I should note, number 5 here, I don't know what its redshift is, that's only 0.7. You see spiral galaxies that are pretty well formed up to redshift 5 or 6 fairly consistently, which is also surprising. Remember, Mo et al. Predicted that they wouldn't assemble until after redshift 1. So we can zoom in on that. One of these interesting things is Maisie's galaxy that Steve Finkelstein named after his daughter. It's a Z of 11.8 galaxy. And you can take all of these individual galaxies. So before I was talking about the characteristic from a fit to many galaxies. Each point here now is a single galaxy observed by JWST by many different groups, hence the many different symbols. Stellar mass is a function of redshift, and we're talking crazy high redshifts even to start here, right? Redshift 6 is all the way back to, first 1.5 gig a year, something like that. And, they're all over the place. There was a concern, okay, are we doing the photometric redshifts right? That's what the colored points are. Lately, we've started to get spectroscopic redshifts. That's what the black points are, and they tell pretty much the same story. Now, the bands are what's expected and allowed. So that dark gray region is disallowed in lambda CDM. You simply don't have enough baryons in a dark matter halo to put a galaxy up here. Of course, to put a galaxy up close to this limit, you need to convert 100% of those baryons into stars right away. That's crazy talk, right? So the real prediction is down at this these blue lines here, the bottom edge of the gray region. So there's no problem having galaxies in the white region in lambda CDM. They really shouldn't be in the light gray region. They could be if you magically turn all the stars into all the baryons into stars very promptly, but you really didn't expect them. And so, of course, we've already experienced a little revisionism. Did we say that was the prediction? No, we meant up there. That might be legitimate, but it doesn't really go a long way to solve the basic problem. Galaxies just shouldn't be there. Galaxies are observed to be too massive, too early. And this is true in the luminosity function as well. So this is the UV luminosity function. That is the number of objects per cubic megaparsec. The data are the points that have worked out. I think this was by Donlin et al. Yeah. This has been a crazy field to keep up with. So this was published late last year. So very fresh paper. I think it came out in December. In January of 2024, I had a different version of this that didn't reach as a high redshift. It showed sort of the same thing, sort of different down here. But you could do stellar mass. It's just happening so fast. But so the data are all up there, and to a first approximation, the UV luminosity function is not evolving with redshift. And you start to see a little decline at redshift 12, those orange points, but there's not a lot. They're all up there. Whereas the lines or the prediction, that's basically that mass assembly, right? You start with little things and put them together. And so the observed luminosity function is barely evolving, where you see an expected, the predicted evolution should be huge. And so if you look at the ratio of those things, at redshift, 9, 10, okay, you're a factor of a few high. You get above redshift 10 and it's an order of magnitude. So that is not just true on an anecdotal 1-by-1 cases, that's what's happening for the population. And so putting all that together, this is now a busy diagram because it includes basically all of the data I've showed you so far. Stellar mass against redshift, all the way from redshift 0 up to almost redshift 15. And some of those high redshift things are probably not true. Imagine editing out a few. Doesn't matter, right? They're not all wrong. The error rate for photometric redshifts is finite, but it's not high. And now we have a number of spectroscopic redshifts. And the lambda CDM prediction was that red band. That's now allowing for a range of different final masses. But what you're seeing is the slow assembly, that linear growth that is fundamental to the hierarchical CDM paradigm. You just don't get that big that fast. And so, sure, you can get to this mass by low redshift, but the progenitors of that thing, even the largest progenitors, should have been small back at redshift 3. And in fact, there are a number of them that are large. So I'm showing Jay's data. I'm also showing some more recent data from JWST. All this has spectroscopic redshifts. Um, and then to get things up here, you need to get going sooner. So these are monolithic galaxy models that got their start after 300, 400, 500 mega years. Time scales appropriate for galaxy mass things in MOND, right? So you need not just a bright galaxy early on, but you have to assemble a lot of mass early on. And that happens quite naturally in MOND, and it's not expected in lambda CDM. Another interesting fact is that these massive galaxies are old. Remember, I showed you before that the stellar mass had been established by redshift 2 or something. If that's really an exponential star formation model or something like these more generalized models I'm showing as black lines here, that means that the stars, most of them formed at even higher redshift and are already old for the age of the universe at the time of observation. And in fact, that is what people are finding. Carl Glazebrook's group has done a lot of work on this. So here you see spectra from JWST, really beautiful data. It's crazy how good this data is. I've spent a lot of time worrying about stellar populations. On the left is sort of anecdotally what you expect for a population as it evolves. So very young, just 4 million years here, 200 million years, a billion years, 3 gigayears. And as that evolution happens, you can see the emergence of the 4,000 angstrom break. And then you can look at the JWST data. These are for galaxies between redshift 3 and 4. And you can see that 4,000 angstrom break, and you can almost calibrate your eye to guess how old these things are. And of course, they fit a more sophisticated model to do that. But the answer is that, yeah, those stars have evolved as you would expect. So here for those high mass galaxies, stellar mass is a function of time, just the first couple of gigayears of the universe here. The big red dots are where they are as observed. You can infer the star formation history from those spectra. So these orange points are when the star formation quenched, which they defined to be when 90% of the stellar mass was in place. The green dots are when 50% of the stellar mass was in place. And I only show this for a few because it gets messy with all of them. But you can see the sort of evolutionary trajectories of things. And these numbers have to do with the times when the thing formed, quarter gigayear, and how fast it quenched, really fast. The characteristic timescales here are 100 million years, a few hundred million years. You have to not just form those stars quickly, which is not too hard to do in lambda CDM, but you also have to assemble them into a single monolithic entity, just one big island universe. That's the hard part in lambda CDM. And if you look back at those TNG simulations, remember they were all still assembling and forming stars at redshift 3. So here is what is predicted. The black points are the high resolution TNG 50 star formation rate in the largest progenitor against the mass. There are some early adopters, right? There are atypical galaxies that are already this massive. So you can find those in the simulations, but they don't look like the data. They're still actively forming stars. It's very rare that you find anything that's even a little bit quenched. And these are just upper limits that don't even fit on the diagram. I just didn't have space to show it on there. So there are things that quenched at early times, and that just doesn't happen in the current generation of models. I'm sure you can fix that in the model. I can imagine how to do it, but it's not what was predicted. Um, and the real problem is mass. There are all sorts of games that you can play to change the amount of light that's produced by a given mass. That's a long conversation, so I'm not going to go into those details. I talk about it in my paper if you want to read about that. But what you're really interested in is the assembly of mass. And so that is something that kinematics can get to you. And so here is the velocity field and position velocity diagram of a high redshift galaxy. This is a damped Lyman alpha absorber at redshift 4.26. So way up out there in time, the position velocity diagram and the velocity field look normal to me. As somebody who's looked at a lot of these things in nearby galaxies, that's what they look like. These authors, Needleman et al., do the inclination correction and get a V flat of 272 kilometers per second. That is a massive galaxy, and it's already that massive above redshift 4. So it's not just playing games with light production that's going to get us out of that. The kinematics are already hinting that there's mass there as well as a lot of light. And that's statistically true. That was an anecdote. There are other anecdotes. Here is the baryonic Tully-Fisher relation on the left, another scaling relation, the dark matter fraction as a function of the baryonic surface density. That's the thing that I discovered way back when, that geez, low surface brightness galaxies are dark matter dominated, right? The dark matter fraction is high. And that is systematic with surface brightness. So those black points are data from my own group. The colored points are from Ginzel's group, binned by different redshift. And basically the rotation curves look normal to me in all these different redshift bins. They just do the same thing as the local data to within any credible estimate of the measurement uncertainty. There are the formal errors bars up in the corners. So these relations were established early by redshift 2.5 and don't appear to have evolved. And to show that further, I have fit the relation for the high redshift galaxies, right? That's plotting mass against velocity, and plotted the deviations as a function of redshift. I've normalized it to the same almost 10 to the 11 stellar masses that I was showing you before. So those black points, those are the data I already showed you for L-star galaxies from Jay's work and from others. That purple line is the same monolithic line. That red line is the same lambda CDM line. And then the blue points now are the deviations of Tully-Fisher. And there aren't any, right? This clump is just as much on the same relation as that clump. So there's no indication of evolution in this relation so far. There's a very recent paper arguing that maybe there was a little bit. Okay, that would be interesting, but you know, it's clearly not following the red line. So the mass is there, and the mass is already assembled by earlier than expected. And I go on about this in some blog posts, which are maybe more accessible than the AppJ paper. Just to finish up, this might also be true for clusters. So here are some of the clusters, proto-cluster candidates, because we're not sure they will become clusters, but boy, they sure look like it. This one, not so much. That one, yeah. So here is the velocity dispersion, right? We have redshifts for all those things. So we can measure a velocity dispersion for where they are at different redshift. Now, most of these will not turn out to be real. We did various probability assessments, and I would not trust the gray points, maybe some of the light blue points. The darker blue points, the big ones, those all have at least 10 galaxies with spectroscopic redshift measurements. So they look pretty real. And they have a median of velocity dispersion around 600 kilometers a second. If you go into, again, Jay did the exercise of going into the Millennium simulation, applying the same selection criteria, and you find similar structures, their median velocity dispersion was a factor of 2 smaller. So again, there seems to be a larger velocity dispersion, which typically means more mass than was expected from the simulation. And just for jokes, I turn that into the corresponding MOND mass, and you do get a reasonable mass for clusters. And it is not crazy to think that a cluster would form by redshift 3 in MOND. That is, in fact, the time scale that Bob Sanders sort of anticipated. How long it takes for a sphere that massive to turn around and collapse. So, you know, in terms of lambda CDM, there is a real problem. We're already gaslighting ourselves into that, oh, we were surprised. We weren't surprised. We expected that all along. Yeah, we should have been surprised. Galaxies got too big too soon. And this challenges the fundamental hierarchical structure paradigm. It is the assembly of mass that's the problem, not the evolution of the stars. But so there are other predictions that have been made. I think reionization started early, talked about that a lot 20 years ago. And before that, exactly when, where it's redshift 15 or 20, right, time redshift gets very compressed in there, but somewhere in that regime. And there's already a growing tension between the Planck estimates of that and just the sheer number of UV photons we observe in the early universe through JWST. Um, Galaxies got big at redshift 10. That's exactly what Bob Sanders predicted a priori, right? That's the gold standard of science. And it's kind of amazing. He said this more than a quarter century ago, and now it's observed. In general, structure forms faster. You get a cosmic web, it just emerges earlier. So signatures of that will be things like a high correlation function for high redshift quasars. You'll infer large bias factors conventionally. You might see things like giant arcs and rings on the sky, basically walls of filaments that are much bigger than you would have expected in lambda CDM. And you get big clusters already at redshift 2. So I will just leave you with this anecdote that in anticipation of these observations, I wrote a blog post when JWST was launched. So that was Christmas 2021. So right at the beginning of 2022, I said, what will JWST? Big galaxies at high redshift. And there are the references for why that was predicted. Then just after a couple of years at JWST observations, Physics Today said JWST sees more galaxies than expected, more than anyone predicted. And it's like, yeah, it's just a testament to the inefficiency of communication. That's exactly what we predicted. So I will leave you with that and be happy to talk about it more. Thank you.
Thanks, Jesse, for a great talk. Lovely. So we'll open the talk out to questions. So please use the raise hand feature. Roger, yeah, go ahead, please.
Yes, according to CCC, you would expect that dark matter decays. Now, I made a very rough estimate. This needn't be right. Something like 10 to the 11 years for the lifetime. Now, that means you'd have more dark matter present in the older the galaxies that you see further away. Now, how does this affect the estimates that you have here? The dark matter would decay, I should say, into gravitons, and so they would just be lost at that point.
So certainly the merger trees I showed were for traditional WIMP dark matter that does not envision such a decay. So if you did envision such a decay, then some of that mass is going to go away over a time, and putting it backwards, that would allow you to pack in more dark matter early on, so that I would think would speed things up.
Yes.
I do not have a good intuition for how much.
Yes, well, I'd be interested to know how that might fit in with your observations.
I would too. And I think that the question is what is the actual prediction there? And it's going to depend on that decay time, right? How much was there initially? How much is left over? So I think qualitatively it goes in the
Yes.
right direction, but I don't
There's
know.
no prediction about how much there should be initially. It's just how much mass you would lose.
Well, I
As
guess I'm imagining that we have a good idea of what we need now. So if you tell me
you'd have
what
to
that,
go back and see what you'd
yeah,
expect.
exactly.
Yeah,
Exactly.
sure. And that would depend on the lifetime. And I did make at one time a very rough estimate, which could easily be wrong, of something like a lifetime of 10 to 11 years.
Well, that's an interesting time scale, right? Because it's longer than the age of the universe, but close enough that we'd notice.
Anyway, I would be curious to know if someone could try and estimate how it would fit in with your observations, which are very striking.
Cool. Thank you.
Okay, thank you. Thank you. Varun, did you have a question?
Yes.
Yeah,
Can you hear
go
me?
ahead. Yes, yes.
So, what is the Stacy? What is the background expansion like in your model? Now, dark matter, contributes to the Einstein equations. It decelerates the universe. Does MOND also contribute to the cosmic background expansion or not?
That is a fantastic question to which I wish I knew the answer. So in the calculations that Bob made and what I've done, you don't have, MOND itself doesn't give you a cosmology by itself. It's not a relativistic theory. So we've just assumed there is a background expansion, and it could look just like lambda CDM, or it could look pretty close to linear, frankly. It doesn't really matter for the things I've said, except where you want to assign a time to a redshift. So I have stuck with the lambda CDM time redshift relation, but that's probably not the right thing to do here. But I don't know what the right thing to do is.
I think this is very important because you see, baryon acoustic oscillations can give us, especially the tangential ones, the radial ones, they can give us h of z. So
Yes.
what we need is h of z in a MOND type theory and compare it with h of z in lambda CDM to see whether just the background expansion can differ. I would be very interested if anybody is working on this or anything at all.
So first, let me agree. The where lambda CDM really shines is things to do with the geometry and measures of the length scale, like the BAO oscillations. And so I think empirically, whatever is going on has to be close to that in terms of the expansion history. Our constraints on that are not great during the Dark Ages, so there is some uncertainty there. Well, I don't want to go too down that rabbit hole because that's a fun conversation we can come back to if you want. But as far as people who are actually working on this, I tried, I failed. I've not come up with a proper theory. Many other people have tried and failed. The best, closest guess that I have seen so far is this ether scalar tensor theory of Skordas and Zlochnik. And they've been able to show that they can fit the acoustic power spectrum of the CMB and the low redshift power spectrum of galaxies. So that's an important reality check. But I don't know what H of Z is, right? There's a lot that needs to be worked out there. So that's promising, but I have no idea how it works out.
Thank you very much.
Thank you, Varun. Anthony?
Yeah, hi. Thanks, Stacey, for a very interesting talk. So I was wanting to ask about clusters of galaxies. You were mentioning those quite a bit towards the end. And I thought that in general, they were quite a big problem for MOND because they don't really lie on what you might think of as the equivalent of the acceleration relation. They just show a constant offset relative to Newtonian by some factor which corresponds to the expected dark matter content of the cluster. So how do you feel about clusters at the moment and how well they fit in?
I hate them. I don't understand them in any paradigm. So you're right. They're a terrible and persistent problem for MOND. So I've written reviews in which I show where they fall relative to this baryonic Tully Fisher. So, you know, the galaxies all fit along there. If you extrapolate that up to the cluster regime, then they all sit off in the way you describe. There is a residual mass discrepancy in MOND, and it's not subtle. It's like a factor of 2 point something that you need extra unseen mass. And people have argued that, well, maybe it's baryonic, maybe it's neutrinos. None of this is really satisfactory to me. And the mass function of clusters looks pretty lambda CDM-like. On the flip side, if you make that Tully Fisher plot I described, the clusters parallel it. They shouldn't do that. They should have a different slope, and this is why the mass temperature relation is the wrong slope for clusters, and people invoke preheating and things like that. It's got the right slope for MOND. It's the normalization that's wrong. The other thing that's interesting is if you think of the famous example of the bullet cluster, it has that beautiful shock wave that you can see. If you look through the lambda CDM simulations, they don't really do that. And I haven't looked through every single one, but if you just calculate the characteristic speed, it's of order of the virial speed, and you just don't get collisions that fast. And, you know, there's a whole literature on just the bullet cluster. Is it possible? Is it not in lambda CDM? And it ranges from maybe to, oh no. And so the prediction of MOND is actually, if you do the same calculation in MOND, you take two masses, let them expand apart and fall back together, it expands that collision velocity quite naturally. And so the prediction was that there would be a lot more things like that. And so I say all that just to say that there are aspects of clusters of galaxies that are problematic for both theories and aspects that actually look legitimately like both theories would predict. And so I do not know what to make of them.
Okay.
Stacy, why the missing baryons are not good enough for the cluster discrepancy of MOND?
Well, so in total, you raise a good point. So we know what we think the baryon density is from Big Bang nucleosynthesis. We can separately do add it up, see how many we see. And there is plenty of slack in that sum to solve this problem. That is, if some of the error budget and where the baryons all were, if that was in the clusters, then there are enough baryons available to explain that problem. The trouble to my mind is what form that they could be in that they would remain undetected. And there are some ideas for that, but they just seem contrived to me. I really struggle to believe any of those things. I hope I'm wrong, but I just don't understand what's going on. There have been a couple of recent papers, one by Federico Lelli and a student, and another by Benoit Famei, looking at what the distribution of this unseen mass needs to be, and maybe it traces the gas, and so it's just something that goes along with the gas. Or maybe it's more dense in sort of a core, like you might imagine if neutrinos had a mass of half EV, they would stick to clusters, but not galaxies. But less than that, they don't really help. So I don't know. I just really don't know. In principle, there are enough baryons available to solve it, but in practice, building a persuasive model that says, oh, I should look for this kind of baryon in clusters in this mass, it's really contrived.
Okay, thank you. And Anastasia, you had something related to say?
Yes. Hi, Stacy. Thank you so much for your talk. I wanted to ask just to follow up on the clusters because when I talked to Amel, he was saying that about their paper with Cordis on the AST solving the clusters problem. So I just wanted to say that so there is a potential with this relativistic right model or theory to actually solve the clusters thing.
Well, that would be great, right? Because we need a relativistic version of MOND, and so if something additional naturally solves that, that would be great. Tobias Mistel looked into that, and you have to exercise and indulge in some fine tuning of the parameters, if I remember the stories right. That basically what worked well for clusters was not quite the same as worked well for cosmology, and if you did too much, you messed up galaxies. So maybe there's a window where that's viable, but I was not encouraged, I guess, by that. But you can turn it around and say that this is something that should inform theory construction, right? So,
Yeah.
maybe.
Okay, thanks.
Related to that, Stacy, so in what all contexts is the workability of MON obstructed by not having a relativistic theory yet, which is convincing enough? Where do we need the relativistic theory?
Well, cosmology especially, right? We
Yeah,
really,
could you please elaborate on that? Like which aspects of
well,
not for early galaxy formation, yeah?
right. That's just what happened. Early galaxy formation is just what happens, assuming MOND is going on in an expanding background, and you don't really have to specify what the expanding background is, just that it's going on. But what is the Friedman equation? What is the history of expansion? I don't know. What is the metric? What is the luminosity distance, the angular size distance, the equivalent of the Robertson-Walker metric? I presume, since we know general relativity is right where it's well tested, and MOND is in a completely different regime, I would imagine, what if there is a grander theory, it has to encompass both. And so I would expect Robertson-Walker and the Friedman equation to be good first approximations to that underlying theory. But I don't know that without the theory, and that's what's missing.
And do we need it for the CMB acoustic
Yes.
spectrum also?
Yeah. So you can't even really talk about the CMB with MOND itself. You can, as I described, give an explanation for the amplitude of the growth structure. That's not hard, but fitting the details of the acoustic power spectrum, well, you mentioned that I did predict the second to first peak amplitude ratio. That is how far you can get without general relativity plus something.
Okay.
And once you get beyond L of 600, then you need something extra, be it dark matter or some kind of scalar field or something. And so that's where you really need GR plus.
And in the early galaxy formation, suppose you had treated the critical acceleration A naught as a free parameter, could you have predicted the value of A naught by fitting the MOND monolithic evolution to what JWST shows?
So the prediction assumed that A naught did not evolve. If you let A naught evolve a lot, then this doesn't happen because you
No,
basically,
sorry, A naught is fixed, but I don't fix it to the Milgram value. I say, okay, suppose I change A naught to 10 to the minus 9 or 10 to the minus 8. Will I still get the monolithic fit correct? I'm trying to say
yeah, okay.
consistency of MOND on different scales.
That's a good question that I have not thought about for a long, long time. My recollection is that there's a little flexibility there, but not a lot. If you make A naught too big, then you're going to lose this feature. But I don't remember a number for that.
That would be a good consistency check because it could not be a coincidence if you picked out the same A naught from the early galaxy formation also.
Yeah, that's a good point.
Yeah, thank you. Thank you. Indranil?
I wanted to comment on like what Roger was suggesting regarding the decaying dark matter, I think. So just want to point out there's some constraints on this. If you look at the CMB anisotropies and use the first acoustic peak as like an angular sort of BAO measurement effectively at redshift 1100. And you combine that with lower redshift BAO measurements which are pretty accurate down to redshift 0.5. That shows the shape of the expansion history in that era is basically following a sort of standard flat FLRW pattern with omega m of 0.3. So there's going to be some constraints from that on how much the dark matter might decay, because you need a certain amount of dark matter to fit the CMB anisotropies. And but you also need pretty much the same amount of dark matter to sort of, in co-moving terms at least, you need the same co-moving dark matter density to persist until very late epochs in cosmic history. So yeah, there'll be some constraints from the BAOs on this model.
Yeah, I mean, I agree. I think the things related to the geometry and expansion history look pretty lambda CDM-ish. We do have a big gulf of what we measure between redshift 2 and 1000, right? So there's a lot to be gained, I think, when we finally do detect the absorption from 21 centimeter against the cosmic microwave background, exactly what redshift that happens and how deep that trough is, contains information about the expansion history at that time. So that'll be interesting when it happens.
That's the measure of the structures at that time, which is important. But in terms of the background expansion, I mean, without making any assumptions about like what exactly happened prior to recombination, you can still use the first angular, the first peak as an angular BAO measurement, because it must be the same feature, physically speaking, that's causing the BAOs at later epochs. So, but you're right. Like that will indeed be very informative when we get to it. Thanks.
We can't hear you, Tejinder.
Yeah, sorry about that. Yeah, Indranin, you have, should I go to the next question?
Yeah, that's absolutely fine. That's just what
Yeah,
I wanted
thank
to say.
you. Xavier, please go ahead.
Yes, I was thinking also on Roger's proposal and in general this type of decaying dark matter ideas in terms of much more direct constraints on that sort of ideas than the ones that Indranin just mentioned. So Stacy, I mean, if dark matter is decaying over time, that immediately would lead to a redshift dependence in the baryonic Tully fissure, wouldn't it? I mean, the amplitude of the rotation curve would be going up towards the past when you have more dark matter. So I'm sure that the non-evolution of the baryonic Tully fissure, at least non-detectable evolution out to the redshift of 2 point something, surely gives you a direct limit on the half-life of any proposed decay for dark matter.
Yes, it certainly gives a constraint. I think we have to be a little careful about what such a theory actually predicts. And I'm not satisfied with what I've seen from lambda CDM simulations, what they predict. So if we're going to make it harder, then it's even harder, right? So in lambda CDM, just straight cold dark matter, the mass is assembling hierarchically. And so already you would naively expect a lot of evolution in Tully fissure out to that kind of redshift that we're not seeing. So I guess I don't know what decaying dark matter theory predicts for Tully fissure in the first place. So I don't know how much evolution to expect. But you're right, there should be some, just because some of the dark matter goes away as time goes on. I mean, this is a more general empirical statement, though, that the Tully Fisher seems to have been established fairly early in the universe, and not to have evolved since then. So what's driving that? Is it if you just have a picture of a dark matter halo that the galaxy's in with its rotation curve, and it's easy to imagine, okay, that formed early and it just sits there. But that's not how CDM works. And I don't know how decaying dark matter works, right? If you put the dark matter halos early and then they gradually decay away, then yeah, you would get the kind of evolution you described. But is that how they form in the first place? Yeah, exactly. I don't know.
Okay, thank you. Sergey, please go ahead.
Thank you for the great talk. So I'm a student, so perhaps my question is a bit trivial to answer, but forgive me for that. But I have a question regarding you're referring to the galaxies being too massive too early. Now, when you refer to the monolithic collapse, what immediately comes to mind is the thought that, okay, you have this high density, the first stars that form, right, you have a lot of those supposed population of 3 stars, short lifetimes, they collapse. So you immediately have this population of early black holes and neutron stars. And so my question is there a constraint on the mass fraction of these hidden populations, or perhaps is it even significant in the first place?
So that's one of the many details I brushed over, and so it's certainly important what that first generation of POP3 stars does. And it's easy to imagine that they did exactly what you described and leave behind a lot of remnants. People have worried about that for a long time, and one of the constraints historically has been the metallicity. If you make a lot of supernovae, you make a lot of metals early, and at some point you overdo it. And we're talking about making a lot of mass in remnant black holes. That said, there are some models that just collapse directly to a black hole without spewing metals all over the place. So maybe that would be a viable way of doing it. You could have a population of primordial black holes. The trick is how do you make them? So yes, you can consider this. I think it's still a challenge to make those things in sufficient number to do what we need to have done.
So, Stacy, just related to that, when Lambda CDM predicted around 1998 that first massive structures would be around Z of 1, did they consider caveats of the kind just mentioned? Namely, if this, and this happen, maybe structure formation go up to Z of the order 10, say.
No, I don't think they did. My experience has been one of continuous surprise. That is, at every step, we've seen more structure in place earlier than we had expected from existing theory. So to give one anecdotal example, 15 years ago or so, I had a program to look at a few clusters of galaxies at redshift 2. My collaborator, Jim Schaumbert, and I had come through and identified these as good cluster candidates by looking at radio sources, seeing if there were other galaxies nearby, seeing if there were redshifts for those galaxies. And in that way, we identified a few of these things that were they looked like clusters. They had a dozen galaxies with redshifts. You could see them all together. And when we asked for telescope time to do this, we got back, well, that can't be a cluster. Clusters don't exist at that redshift, right? That was the attitude. It was so embedded in how we were thinking. And we just get surprised like that over and over again. So if you go back to a model like MOSE, which I picked because it's sort of a touchstone for Lambda CDM, there's nothing like this that's really going to change that answer. You could push things back some, maybe redshift 2, but you're not going to get to redshift 10 that way. You're just not.
Okay, and then suppose JWST did not find the galaxies that Sanders predicted, would we have said today that, okay, now MOND is ruled out?
Well, that's a really good question, and I think not. I mean, that's the prediction, but is it exclusive? I don't know. I haven't thought that through. I think you have to get some things forming that early. The question that Mom does not give you a clear answer on is how many. It just says it can happen. It doesn't say it has to happen every single time. Um, and I would expect galaxy formation to be inefficient in MOND because you need a large spherical region to all be in the low acceleration regime for this to work. But of course, the early universe has lumps and bumps and flows and things going on everywhere. So in general, I don't expect that to be satisfied very often. Right. So I would have been surprised if there were zero, but I don't have a good expectation for how many.
Okay. So for that, do we need the relativistic MOND, or we don't need that for?
Not really. What we really need is a Mondian simulation with gas physics in an expanding background. I think that would go a long way to doing that. And some people are working on that, but I don't know at the level that'll resolve. It's a huge problem of resolution that even the giant lambda CDM simulations that have been done struggle with at that high redshift, and certainly nowhere near as much investment has been made doing that sort of thing in MOND.
So, but even if it's relativistic MOND, we would keep an equivalent of a dark energy in the background, giving omega of dark energy about 0.7. That is okay to keep, right?
Yeah, I think so. You know, you could imagine it would go up so that you know, the simplest such model, you could have 5% baryons and 0.95 lambda. And that's not exactly, well, that actually fits the CMB grade out to L of 600. And it's not terrible for the supernova, but I mean, I just treat that as a big unknown. MOND itself doesn't tell me the geometry. What we call lambda is basically a geometric fudge factor. That's what we need to get the geometry to work out in either theory.
Yeah, actually, at least some work indicates that MOND is a mediator between a de Sitter geometry at the horizon and GR at high accelerations. So the buffer, which is normally done using cold dark matter, is now being done instead using MOND, but on the cosmic horizon scale and on the high acceleration end, it is pretty much the same story as in the lambda CDM.
Interesting. Yeah, no, I'm intrigued. So I remember last time there was a bit of discussion just that I had to go about the coincidence of A naught being close to the speed of light times the Hubble constant. I always thought that was a bit of numerology because the Hubble parameter has to evolve and it doesn't look like A naught does, at least out to Z of 2.5. On the other hand, there's a similar coincidence with the cosmic acceleration scale, basically how big lambda is, and that doesn't evolve. And so that is more suggestive of a connection, that we have these two mysterious accelerations, and it would really be nice if there were a theory that explained both naturally.
Yeah. Yeah, it's not impossible that the Milgram A naught and the cosmic acceleration are as a underlying theory related to each other.
Exactly.
Yeah, Bunt.
Thank you for the great talk. I have a question concerning the difference in the galaxy formation history. So on the lambda CDM, we would have expected to see relatively young galaxies, so freshly forming galaxies, and even maybe population 3 stars, to get back to the previous question. So this should be different in MOND. So basically we have to wait for an even larger telescope to see the very first galaxies and population 3 stars, or can we also expect to see population 3 stars with the James Webb Telescope?
So the very first things, right, the redshift timescale gets really compressed. So I think, I mean, and I should step back and say I describe MOND in terms of a monolith, but it starts from the same initial condition of these small perturbations. So really, it looks monolithic because everything happens. It's still hierarchical. It just all that happens super fast.
Okay.
And so I think that's all after redshift 20 is so I think there is a chance to see things around 15, 20 of that sort of thing.
Okay.
Yeah.
Thank you. Thank you
Thank
very
you.
much.
Anthony, go ahead, please.
Yeah, I had a couple more questions. The first is on the radial acceleration relation in sort of not thinking about high redshift, but where we've got really good data in the nearby universe. And the people doing simulations, they presumably can work out something similar for what they get from their simulations. And we know that they get some galaxies that look really very similar to what we see today. They're doing extremely well now in simulating spirals and ellipticals. And what they say is that actually you get something pretty close to this radial acceleration relation just naturally from the cold dark matter approach. So I'm just trying to understand the extent to which, although it looks, amazing how it lines up on this one prediction, you could still get that within CDM.
So that is certainly a common claim. I do not find any of those claims to be satisfactory. You touch a nerve here because I, been trying to get them to do this for 20 years. I wrote a paper in 2004 saying, okay, never mind Mond, here's the data, please explain this. And I literally had those people shouting at me in conferences, we don't have to explain that. It's Mond. And I'm like, no, it's just the data. And now 20 years later, I've told them what they have to explain. Oh yeah, we can do that. Yeah, come on. That's rubbish. And if you look at those claims critically, they do not withstand one shred of evidence. So for example, you are correct that they've gotten really good at making galaxies that visually look like galaxies. If you look at their mass models, they look nothing like a real galaxy's mass models. They tend to be very dark matter dominated, even for the highest surface brightness cases. They struggle even to give you a flat rotation curve. They almost all go down. It doesn't add up. But you're right. If you look at the radio acceleration relation, that's a log-log plot over a law scale, so it hides a magnitude of sins. And so you really have to look at the residuals to see that they go wrong. So this is why Michela's work is really important, I think, because that extends the relation to much lower accelerations. And all those things have some curvature that kick in by then, and you just don't see that in the data.
Thanks. But I had a question about that as well, actually, the lensing result.
Yeah.
Because it's very striking, but aren't you having to make an assumption there about how light behaves in a Mond background? Because you're trying to use the lensing itself, which is normally explained, caused by the dark matter, but calculated within a full GR context to derive results for Mond, which, how do you know how the light behaves? So that's what I'm trying to ask.
Sure. And that's a really good question in Mond and Milgram's written papers about that. But what we're doing is not using Mond. We're just asking what the potential is that does that light minting. So it's strictly a GR exercise. And we get that inferred acceleration curve, right? There's the radial acceleration relation is just an empirical thing. I don't know about Mond. It just comes out looking like Mond. Okay, so I don't use Mond in the data analysis.
Okay, but presumably a relativistic theory of Mond might tell us that things behave differently.
Yeah, that's possible. And then you know if it does the wrong thing there, then that theory is wrong. We've had a lot of wrong relativistic Mond theories.
Yeah.
So yeah, no, you're right. That is an issue. My concern about the gravitational lensing. Yes.
Moti is saying something. Go ahead, please.
Yeah, I mean, all relativistic theories of Mond proposed today, beginning with Teves, bimetric Mond, all of them predict the same behavior for lensing as in GR, namely that famous factor of 2. That is, you can simply use the Mond potential for those galaxies and calculate the bending, assuming this famous factor of 2 that also appears in general relativity. So the calculation is consistent with all those relativistic Mond theories. I mean, they have like bending that should give consistent, maybe put it this way, suppose you determine the potential of a galaxy from rotation curves, namely using massive test particles, and you use this potential in the context of relativistic theory, just assuming this, using this factor of 2, you should get, this predicts correctly what lensing should do. So there's no problem here.
So I would add empirically, the thing that worries me about our own lensing results is that we do have to impose an isolation criterion, right? We want to know the potential of just one galaxy and not stuff further out. And so when you talk about hundreds of kiloparsecs, it's actually hard to find galaxies that are isolated. So we've done that as best we can, and we get the result we do. If we relax the criteria, then we see the signal of that. But, you know, you could maybe get different answers making different cuts on the data. Still, that's what we see. We just do our best job doing that isolation criterion, and isolated galaxies tend to have flat rotation curves way the heck on out, further out than you would expect from a conventional dark matter halo.
So I agree, the results are very striking. Just one more question, if I may. On the determinations of the mass of these very early galaxies, when the first James Webb results were coming out, people were, working on it, were very hesitant indeed about the mass assignments, and said it would take, a lot more time to sort out exactly what we were seeing and how massive these galaxies are. I mean, you didn't really stress that as a possible problem. Do you believe that that is now okay? We've had enough time to understand what's going on.
In a nutshell, yes. So I had actually, I just published this paper. I'd actually written all the pre-JWST material so that as soon as it came out, I could add that on and say, here you go. And of course, you remember there was a feeding frenzy of that at exactly that time. I had exactly that concern. I did not believe it. And so it's taken 2 years of waiting and vetting and seeing. And I'm sure there are still a few cases that are wrong. But no, I don't. If you look at my AppJ paper, I go through all these, well, it could be a different IMF. Well, it could be this, it could be that. But I don't think so.
But Stacy, you seem both to be talking about stellar masses, right?
Yep.
But as you showed from kinematics, you don't need that. You have direct evidence for the total mass. So that's not questioning, at least for those that have kinematics.
That's right, Marty. But to be fair, the kinematics only don't go as far back as the JWST stellar masses, right? So there could still be a question of stellar mass at redshift 10.
But there is an issue already with those galaxies, isn't there? That do have kinematics.
Yeah, that's right. And they're pretty early, so I don't see how you can get away with it. But it has been a struggle to get to the point where we believe the stellar masses, and there are legitimate questions on the way. The kinematics are still at an earlier state. So I think the writing is on the wall, but the data can continue to improve.
Thank you. Thank you. Anthony, could I ask you, what is your take, lambda CDM versus Mond, which does better where? I mean, I would be very happy to know your thinking at the moment.
I've become more and more interested in Mond over recent years, primarily from looking at how well the radial acceleration relation enables you to sort of sort the data for galaxies and make sense of what you see. So I find it absolutely fascinating. But theoretically, I'd love to see how we can actually have a fully relativistic theory where we can work out all these additional things, particularly the microwave background, particularly the development of perturbations leading to these early structures. No, I think it's absolutely fascinating, and I pay more and more attention to it.
Yeah, so my view is that the relativistic theories that we are looking for should somehow fit also very well in the framework of standard model physics or particle physics and general relativity, not just a modification of general relativity, which is okay at the phenomenology side, but we have a SU3 cross SU2 cross U1 particle physics. How should we enhance that so that it gives us something like relativistic MON as a Yang-Mills gauge theory, for example? Would you agree with that kind of a viewpoint?
I think we're some way off that. I think things like the ether scalar tensor theory are getting closer to having a proper relativistic MOND. So that's the sort of line which I myself am interested in pursuing at the moment. Made a modest start with Einstein ether, looking at spherically symmetric solutions in that. But there's a long way to go in all of these. But that to me is the first stage. Having something that probably has to bring in what people call breaking a Lorentz covariance, just means you have a fixed background time-like vector. That seems to be key to getting a relativistic theory. That would be the first line that I'd want to explore.
But still, by itself, that doesn't get us close to particle physics standard model.
No, I think strongly that the link between A naught and the cosmological constant is a real one. I think that's not a coincidence. I think that's one of our biggest clues. So that's very important, but I don't see at the moment a particular time with particle physics.
Yeah, just to bring in my own picture, what we have been pushing, I think I mentioned this before also, the relation between MOND and general relativity or relativistic MOND and general relativity is analogous to the relation between electromagnetism and the weak force. Beyond some scale, one dominates over the other and vice versa. So we are trying to make an analogy that electroweak and gravimond are sort of, and A naught is the kind of order parameter which decides on the gravitation mond side, and over there it is, the evolution, say, of the fine structure constant and the Fermi constant as function of energies. At some high energy, they would become equal and cross or something like that. So it would be nice if we push this into the particle physics Yang-Mills gauge theories domain, because that then also brings an associated gauge boson, which one can say, okay, I need to go and look for this in the lab, say. So right now we don't quite have a quantum theory of relativistic MOND where we can say, okay, like the graviton, I have a new associated gauge boson. Yeah, just some thoughts. Thank you. Yeah, okay. Yeah, more questions. Please, Stacy, I had one more question. Just to bring in gravitational wide binaries, Xavier was here some time ago. Would you regard that as complementary support for MOND in an independent scale?
Well, so yes, in principle. I think one needs to be clear on which theory predicts what, right? It's not obvious, and maybe Marty can comment on this, it's not obvious to me that modified Poisson, modifications with the Poisson equation do the same thing as modified inertia. I think if there is a positive detection of a MOND-like effect, that would be difficult to understand in terms of dark matter, because these are scales where the dark matter is not supposed to do it. But as Xavier wants to say something, so you should ask the expert.
Please go ahead, Xavier.
Just a brief comment regarding what you just said. And it's that at the lowest order level, at zero order level, what has been confirmed now with wide binaries is that there is a signal at an A0 scale. So the A0 scale is appearing there as well. The details of what exactly is going on, I agree, depend on whether you have regarding predictions, will depend on whether you have a sort of a modified gravity or a modified inertia or whatever. The details of the transition functions and external field effect dominated regime is much harder to calculate and so on. But for starters, you see an A0 scale at the same level at which it was calibrated in Galaxies, more than 8 or 9 or 10 orders of magnitude above. So I think that just having A0, the A0 scale popping up at solar mass scales is extremely suggestive and to me quite surprising, really.
I agree. Can we go ahead and say that the A0 scale is popping up in JWST galaxy data?
Well, I think that's certainly the implication of what I was just saying.
So that would give us three different scales where A0 shows up to be essentially the same number where it didn't have to be.
Yeah, that's right.
Thank you. And my next, Xavier, something more to say?
No, sorry, I just forgot to
okay. So question, Stacy, for you or anyone else who would like to comment. Are there any ideas on, say, testing MOND in the laboratory, or is it simply impossible because the accelerations are too low?
Well, Monty's the real expert here, but basically it's impossible. There was one suggestion from Iorio that if you put a sensitive device at just the right spot at just the right time, then all the vectors would cancel out and you'd get a few moments of Mond-like effects in your laboratory. It had to be at the latitude of Greenland or something crazy like that. But if you simply set up an Iat-Vosch type experiment and measure interparticle accelerations, that's great, and that's been done below A0, but you don't expect any signal because you're sitting on the surface of the Earth, so you're way inside the Newtonian regime, even if the interparticle accelerations are tiny. So, you know, that would exclude a Mond-like theory that is not Mond, that predicted Mond notions, but Mond predicts no signal there, and they see no signals. So yeah, really, you want to send that thing out into the depths of intergalactic space. And so if you have a big rocket and want to wait 1 billion years, then we can do that experiment.
Another remote possibility is that if MOND says a gauge theory, a Yang-Mills gauge theory in the relativistic limit, the associated gauge boson is a prediction for particle colliders, if that ever happens.
Well, I think it's certainly good to think about additional predictions that would come out of more developed theories. And so, I don't know. But it's really hard to test experimentally on the ground.
Yeah, I agree. Yeah, I think Indranil, you want to comment on?
Yeah, okay. I mean, while you were discussing tests of MOND, I thought I'd point out one of the more promising sort of laboratory tests, if you will. It's a spacecraft test. And this one is exploiting the fact that the regions Stacy was talking about, where there's like cancellation between the Earth's gravitational field and the sun's, leading to a saddle point, if you like, or a zero acceleration point. The problem in that case is the tidal stresses are so large, the region in which the accelerations are small is very, very tiny. But if you were to go to the outer solar system, then this saddle region becomes much larger between, in particular, Neptune and the sun. So if you were to get a spacecraft to sort of the inner edge of the saddle region between Neptune and the sun, and let it sort of freely fall across it, that would take like over a week. and it would allow some very strong tests of MOND. So essentially, a tabletop experiment to test MOND would give anomalous results if it was in the Sun-Neptune saddle region. But unlike the Earth-Sun saddle region, which is barely big enough to fit a tabletop, the Sun-Neptune saddle region is like 1,000 kilometers big or something. So it's very much more promising. And also in the case of Jupiter Sun, it's also more plausible. But in the case of the Earth Sun, it's not really practical to do this kind of test.
Thank you. Thank you. Yeah. Anthony, please
Yeah.
go ahead.
Can I just ask about that sort of experiment, to the extent to which you don't really know what the predictions are because of the external field effect? That maybe, doing it in a special place like the solar system, which is in our region, the galaxy and so on, that you can't really make a proper prediction. This is something we haven't sort of talked about so far, but it does seem to me a bit of a problem that we don't generally know how to deal with the external field effect.
I guess in that case it matters because you can get to the point where the Newtonian gravity from the sun and the rest of the from the sun and Neptune cancel, and well, you can shift the point slightly to also cancel the gravity from the rest of the galaxy as well. But subtle details such as whether you want the Newtonian gravity to be zero or whether you want the actual gravity to be zero, in theory, that I haven't looked into how much that detail matters. But in principle, you shouldn't be having to worry about the external field effect because you should be going to a point where it cancels.
Well, I think the point is well taken that you have to be very careful about what you actually predict. But it would also be great to do the experiment, right? Go and see. At the very least, you would exclude large swaths of theory space that way.
Thank you. I like to often pose this question for amusement. Suppose Newton was presented both with Kepler's planetary data as well as galaxy flat rotation curves. How would he explain them? Would he say inverse square law for solar system and dark matter for galaxies, or would you like to just for fun, Stacy, say something there?
Well, certainly I have contemplated that question. I do not care to put words in Newton's mouth. But what we do know is that he was presented with Kepler's law, and he came up with the inverse square law. And he didn't understand where that came from at the time, right? It took a long time for that to become clear. So the situation is certainly analogous in the sense that we now have an effective force law in galaxies. And so I don't think he would have looked at that and come up with dark matter. But I have no idea what I would like to know what he would have come up with. So,
Yes, in that respect, I think we don't have to put words into Newton's mouths. We can actually read what he actually said. And I'd like to read, if you can spare a minute, the
Please go ahead.
preface,
Yes.
the preface to the second edition of the Principia. Okay, and there's a paragraph there that's extremely telling, because, well, he's actually going on about not dark matter, but it applies to dark matter just the same, no? He says, by going on from simple things to those which are more compounded, they certainly proceed right. If in bodies, if they attribute no other properties to those primary affectations of the particle than nature has done, but when they take a liberty of imagining at pleasure unknown figures and magnitudes, and uncertain situations and motion of the parts, and moreover of supposing occult fluids freely pervading the pores of bodies endued with an all-performing subtlety and agitated with occult motions, they now run out into dreams and chimeras, and neglect the true constitution of things, which certainly is not to be expected from fallacious conjectures, when we can scarce reach it by the most certain observations. Those who fetch from hypotheses the foundations on which they build their speculations may form indeed an ingenious romance, but a romance it will be. It will still be. So that's part of the preface to the second edition of the Principia.
Could you summarize that, Xavier, in a couple of lines, just to, because sometimes his English is heavy.
Well, he's actually going on about the Cartesian vortices, which was the competing theory at the time. No, people didn't like action at a distance, and the sort of standard picture at the time was that there was these vortices which Descartes had postulated, which carry the planets around, and nobody has ever seen or detected. These were sort of just like dark matter, completely invisible and completely undetectable. So his point was, if you can come up with undetectable entities that explain your observations, but if they are undetectable, you're just concocting a fantastical idea. No, it's okay, fine. It can explain what you observe, but it has zero predictive power, just like dark matter. And in terms of rotation curves, Stacy has made this point many times. Yes, you can explain the rotation curve of a galaxy by invoking the correct dark matter halo, but whereas Mond predicts, once you've observed the brightness profile, Mond predicts what the rotation curve should be. There's no equivalent prediction in dark matter.
I agree. I think I was thinking one challenge for Newton would be to come up with an interpolating function. It's always very interesting that we have m by r square in Newtonian, and the deep Mond regime is square root m by r. So no Coulomb field would sort of behave as 1 by r square. So I hesitate to modify the left side of the Poisson equation to get a 1 by r out somehow. I would leave the left side of the Poisson equation as it is and say something about the source. So square root of m is still doable, but 1 by r is very challenging. So Stacy, you have any thoughts on that?
Well, no, I agree with what you had just said. I would, since we were talking about Newton, say my favorite quote in this context is when he introduced the inverse square law. He was careful to preface it because, as Xavier says, people were uncomfortable with action at a distance. So he said, everything behaves as if was the inverse square law going on. He was like, I don't know why, but that's what it looks like. And that's really what I'm saying about galaxies now. It sure looks like Mond, as if that's the effective force law. And so to me, that says something fundamental is going on, that you're not going to get it out of concocting a bunch of weird galaxy formation things. But I also don't know what that fundamental thing is.
Yeah, I agree. More questions, please?
Can I just add something very quickly there to Jinder? I think the analogy with the situation with the Cartesian vortices and Newton's pushback against those is actually, in some ways, it's even more favorable to Mond in this sense, because at least in the case of the Cartesian vortices, the proposal was coming from an absolutely kind of fundamental conceptual requirement, as the Cartesians saw it, that dynamical effects had to rise via contact transformations, because they had an underlying view about the kind of fundamental continuity of the medium of transmission. But there's nothing, as it were, in the background with lambda dark matter, standard cosmology, that's based on that kind of kind of fundamental conceptual desideratum. It's just that it happened to be the predominant game in town at the time that these effects that were predicted a priori by Mond suddenly came to people's attention. So I think in some ways the situation vis-a-vis Mond and lambda d dark matter is sociologically, or may say in terms of broader conceptual terms, more favorable to Mond than in the case of Newton's anti-Cartesianism, which, I mean, you're right. I mean, Newton was absolutely right. The whole point about hypotheses and on finger, he had no account of the origin of the inverse square law, but he was absolutely honest. It was clearly the way in which Kepler's laws could be accounted for in general sort of mathematical structural terms, derived from a more fundamental principle. But there was no account, there was no suggestion of what the mechanism was. And we're in the same position with Mond, of course, but
Yes, I agree. I agree.
yeah. So
Also, I think as Stacy mentioned early on in his talk, it's very important for cosmologists to take note as to what particle physics is saying about potential dark matter candidates, and the situation is not good. I mean, nothing in beyond standard model physics stands out today, except maybe the current favorite, say the axion, the very light bosonic dark matter. There's nothing convincing from that side, and I think we have to play the two games together, particle physics and cosmology. As cosmologists, we cannot say that the candidate particle nature of the dark matter is somebody else's problem. That doesn't cut. Yeah, Bernd, please go ahead.
Just briefly to add something on history, we had something like Mond earlier at the end of the 19th century when people were trying to explain the orbit of Mercury. There were also some modifications to the Newtonian dynamics put forward by Hill, for example, or by Newcomb. So we had something like a Mond-like situation earlier, where also people were looking for a kind of unseen planet, Vulcan, and there were also people trying to modify Newtonian dynamics. This was somehow getting lost in the history of science. Well, probably not for Michael and for the historians of science, but it didn't transpire to the whole scientific community. And then Einstein came, and we got a relativistic version, which is now called general relativity for the Mond trying to explain Mercury, and maybe something like this will happen.
But is it not true that if you have a 1 by r cube correction to inverse square law, say by the oblateness of the sun, you can explain the precession?
Yes, this was one of these early modified Newtonian dynamics. I'm just using the phrase we would use today because at that time they didn't call it that way, but this was the way. So modify the inverse square law to explain the orbit of Mercury. This was something people did try. Yes, and then Einstein came and explained it nicely and perfectly. And, yes. But we had such a similar situation.
Over there, it was only one planet, but now we have.
Yes. The situation is different. They were looking for one planet and not a whole bunch of new particles or an incredible amount of unseen mass. This is different from the situation we had with a Vulcan. But what is similar is the why people were looking for Vulcan, because Newton's mechanics was successful, and it was also successful in predicting a new planet, Neptune. And then from this experience, they concluded that we have to look for another planet. And the situation is similar today with a very successful theory of general relativity. And people were quite successful with explaining anomalies by inventing new particles. Started always the neutrino. And so people got used to explaining anomalies with the new particles. This is a situation similar to the situation we had with Neptune and Vulcan in the 19th century.
I mean, I would say that today, in my opinion, we are seeing problems for general relativity on 3 different cases: JWST, galaxy rotation curves, and wide binaries. I mean, for me,
yes. We have many more astronomers and we have many more instruments than we had in the 19th century, so it's easier to get more, let's say, gaps in a theory than we had in the 19th century. This is correct. So we have way more researchers and way more equipment and way more observations actually than we had at that time. But how do you call it? The psychology is similar. We had earlier very successful Newtonian dynamics, which also had a successful prediction of an unseen planet, in this case Neptune. And for, let's say, in the 1950s and 1960s, we had the establishment of a very successful theory of gravity, general relativity, and all the anomalies which showed up in particle physics could be explained in most cases by finding new particles. And so the community got used to this kind of explanation. This is what I wanted to say at that time. And that's maybe why they put so much emphasis on looking for new particles instead of modifying gravity.
Yeah, and WIMPs were a well-motivated hypothesis, right?
Yes,
I mean,
yes. Also from a purely theoretical point of view, because at that time people hoped for supersymmetry and unification of forces, and WIMPs naturally show up in supersymmetric models.
Yeah, exactly. And I
So
believed in WIMPs as much as anyone. It's just not what happened.
That's what happened, yeah. So that's all I wanted to say. It's normal also in the history of science for something like this to happen. We get used to our old successful ideas that it's hard to
maybe lastly, Stacy, what would you seek in terms of MON progress to make the case for the theory stronger? Would that be a relativistic MON which is convincing?
Yeah, I think really that's what needs to happen is on the theory side, that we have a theory that explains both GR and MOND in the right limits, and ideally has some compelling physical reason for being that way, right? I mean, that feels to me like what's missing, and the closest suggestion I've heard is something to do with Mach's principle, but I haven't seen a viable mechanism for that. But why does MOND happen? What is the physical reason for A naught?
Yes. I did write to you, Stacy, about that. It's the comparison with electroweak, that if a cosmic inflation-like phase continues all the way up to the electroweak symmetry breaking, then at that time you can predict the acceleration of the de Sitter universe in comparison to the electroweak symmetry breaking scale, and these two are tied to each other. If the electroweak symmetry breaking scale is around a TeV, the Milgrom acceleration would be around 10 to the minus 10 and very close to the cosmic acceleration. So there is some attempt in the literature, but maybe that's not of interest to particle physicists because we don't predict a dark matter candidate. We predict a gauge theory, which looks like MON. And for me, this is very fascinating that the quantum number, the charge quantum number is square root of mass. And we found good reasons to have a gauge field in which the quantum number instead of electric charge is square root of mass. And that is actually buried in particle physics. That has to do with the ratios of the masses of the electron, the up quark and the down quark. That ratio is 1:4:9. And the square root of the ratio is 1:2:3, which is the inverse of the ratios of the electric charge, which is 3:2:1. So it's not a coincidence that the square root of the masses of the electron, the up quark and the down quark are 1:2:3. So that was a motivation for us to invent a new gauge field whose quantum number is square root of mass. And then we saw that, oh, that is what MOND also needs. So we have to look for some connections with particle physics to come up with a MOND-like gauge field.
Can I comment on, Stacy, your answer that you said that you think that this might actually, so do you actually think that this might solve the debate in a way? Because you also write about the incommensurability stuff, right? And so, and then you also don't agree even on observations sometimes with Simon White, for example, in your debates. So I wonder how much how much would that even address the kind of the problem of the who is right and who is like more adequate in describing the physical phenomena,
Right.
if you can't agree on observations.
So yes, first we have to agree on what observational reality is, right? And I presume you're alluding to the weak lensing disagreement there, yeah. And so yeah, that's why I didn't want to push that too hard. There is some debate about what the right answer is there. From my own perspective, MOND works too well to be some kind of coincidence of feedback in dark matter models. That's just a non-starter, really. And I know that. I'm comfortable saying that because I've worked a lot on trying to make it work. It doesn't. It just doesn't. Can I say it cannot ever? Well, of course not. But you know, most of the claims that I've heard that, oh yeah, we can do this with a simulation, are just reproducing elaborate versions of models I tried and rejected as obviously unworkable a long time ago. They haven't caught up to where I was in 1998. And so, you know, it's not on my own part for lack of effort to make it work out for dark matter. And there's a fundamental fine-tuning problem with trying to make a Newtonian galaxy plus a Newtonian dark matter halo add up to a single universal force law, which is basically MOND. It just doesn't add up. But that's my perspective, right? So, you know, you do have to worry about everything else in the universe and you want to explain all that. And I think MON does a better job of that than most people appreciate, but there are things like clusters it doesn't do well. And so it really depends on how you choose to weigh those different lines of evidence. And that is still a fundamentally human choice, right? We are choosing to weigh these different lines of evidence. And, you know, I choose to weigh things based on my experience, struggling to make dark matter work and it not. And then Mon just says, oh yeah, that's what you should expect. Other people haven't had the experience and their experience is as valid as mine. So, you know, I think we're kind of lost in the woods as to the sociological question. So I think two things have to happen. One, the theory thing, we thought we would like a great, perfect theory of MOND. But before that, people have to convince themselves that dark matter is wrong. If it is, right? And I believed in dark matter before I met MOND. I was convinced that there was a problem, a fine-tuning problem for dark matter before I became aware that MOND predicted the things I was seeing. So I'd already worked through that. Geez, this is a problem. And then, oh, by the way, here's this other theory, predicts this thing. Okay. But, you know, nobody's going to just up and abandon the standard picture unless they have really good reason to. And so I think everybody has to decide for themselves what criteria they would set for no longer believing in cold dark matter or whatever flavor of dark matter you like. And part of the problem is that people don't set that criterion. They've already accepted it exists and that it doesn't exist, doesn't enter their darkest nightmares, really. But then it's not a testable hypothesis, right? So you really get into deep questions about what the definition of science is at that point.
Stacy, may I add something?
Colin, please go on.
Yeah. Stacy just described how, you know, his opinion shifted as a result of looking at the evidence, the science evidence. But, you know, you had really had a vested interest in dark matter, had you?
I had a prediction, and my prediction was wrong. Yours was right.
But it wasn't really like other people who work on dark matter with huge vested interests. So, you know, I used to say that people, those people believe in dark matter, work on dark matter, not because they believe in dark matter, but rather they believe in dark matter because they work on dark matter. So obviously, you know, there is a huge, how shall I say, vested interest for people, you know, for jobs, for what they are going to do, and so on. So, yeah, they cling to evidence that they want to justify something that they, you know, made up their minds about, irrespective of scientific evidence. So it seems. I mean, okay, it's natural. It's human. I don't even know how to tackle this. But yeah.
Thank you. Well,
there's a good Upton Sinclair quote about this, that it is very hard to make a man believe something if his income depends on him not believing it.
Yes.
Exactly.
Yes.
Say very quickly, it's known in economics as the as the fallacy of sunk costs.
Yeah, Pavel has his hand up. Please go ahead.
Thanks. I've been following the discussion. It's of course very, very nice to see this fairly large group discussing these very important issues. And thanks, Stacy, for this very nice talk. And on the existence of dark matter, something which maybe should have come up is that one can test for its existence just by applying Chandrasekhar dynamical friction, right? I mean, it's a very trivial, simple test, and with the Gaia data we have today on the motions of the large and small imaginary clouds, as well as other systems, the existence is completely ruled out. I mean, it's a much more than 5 sigma falsification of the existence of the dark matter particles. It's been published. And I just don't understand why this is not being brought up much more, because this focuses the discussion absolutely away from any dark matter approach. I mean, it's like lunatic to still continue with that, because it's been completely ruled out to exist. And the way that works is you just look at the current motion vectors of the large and small imaginary clouds, their relative positions to the Milky Way, which we know very well. And so we can calculate backwards in time to trace the orbits, compare with the star formation histories of the large and small imaginary clouds, as well as the necessity to produce the imaginary extreme. And all of that simply absolutely does not work if there's dark matter, because they merge. They just merge away. There's no chance to make the imaginary extreme. There's no chance to make the correlated star formation history over the last 3 billion years, which has been now measured with stellar population aging, which is sufficiently accurate to do that. And this issue of dark matter is just off the table. It does not exist. Yeah, so we have to discuss MOND. We have to look at the foundations of where MOND comes from. There's just absolutely no other option. And anybody still entertaining the concept of dark matter is just not physical. That's unscientific thing to do today. I just wanted to bring this strong statement here. And it should have been brought up by others, I thought, but
I was wondering if some of you could at this stage write a note pointing out to these 4 or 5 observations, independent observations, which are problematic for dark matter: JWST, gravitational wide binaries, of course, flat rotation curves, dynamical friction and motion of Magellanic Cloud, and probably also your work, Pavel, on the tidal tails.
Well, the tidal tails too, sure, exactly. I mean, that just tells us that, yes, gravitation is definitely not Newtonian. It does behave like MOND, yeah, that's basically it. Even on the scales
a paper that some of you who are experts on this get together to write, to, bring it into public focus. That, okay, now there are...
Sure, but this has been written up, I mean, there's been like Kropp et al. 2023, there's a fairly big review on all these things. It's all there in the literature. There's the test using dynamical friction has been published very, very clearly. It was not easy to get it published because the referees go mad when they find that there's evidence against dark matter. It's like impossible to then continue a sensible argument. Then the editors fail because they should have been filtering this. So it's very hard, but it's been published, and the situation is crystal clear. It is, if anything, MOND, or something like MOND, but it's basically MOND. It's just
I agree.
Yeah,
Sorry, go ahead, please. Go ahead.
Just saying that Pavel has written quite a few reviews that describe all those problems with dark matter. I mean, so
yeah,
I agree.
And it's just like Stacy. I mean, me too. I didn't enter this field wanting to disprove dark matter or anything. I mean, I started working with dark matter, but it's just not the right theory. It doesn't work. Yeah, and I'm very impressed by Stacy having actually aired this a long time ago by having looked at the data. It's very, very rare these days to find astrophysicists who actually look at the observations and from that make deductions which are pointing in the right direction, rather than saying the data can't be right because we know that the theory must be doing this or that, which is the dominant community. That's what the dominant community is doing. Yeah, but
Yeah,
the dynamical friction rules out dark matter. That's the message here. Yeah, and you can go and check the papers. You can do your calculations. You can do it on a piece of paper. Even the dynamical friction decay time scale is short for LMC SMC. I mean, you can do that in kindergarten. Yeah? So continuing to discuss the existence of dark matter is at this point unphysical.
I agree. Yeah, I agree. We don't know how to overturn the sociological situation.
Yeah, I know. Well, you
Maybe,
can,
maybe as a community, if we come up with a good relativistic cosmology with Mon,
no, well,
that
sure,
might,
yeah, that is absolutely necessary. However, the way to do it is to expel anybody who still keeps on talking dark matter. That's just rubbish. It's just nonsense.
yeah, but
No
if
point in doing it.
if you look at the archive HEP phenomenology, there is a lot of temptation to make a beyond standard model physics theory and say, okay, here's my new dark matter. Every day there's one new
I mean,
dark matter
sorry,
candidate.
that's
What
what I
can
mean.
we do? They are
Shut
not
up.
looking at astrophysics.
That's not physics anymore. Sorry. I mean, and that's what you have to communicate to the young people. I mean, if a young person comes to me and tells me something about dark matter, I just throw them out of the room because it's just simply not physics anymore. And this has to be communicated to the young people so that they
Yeah,
understand that that is not the right way to do research, and it is not. Yeah,
I agree.
yeah, that's
Yes, if I may weigh in on this, on the communicating to the young people, I am one of those young people. I did attend this semester the lecture on cosmology, right? So at my university in Bonn, so the same one where Pavel has his professorship. And essentially in the sort of communication of the entire like Lambda CDM framework, the only issue that was ever brought up is the Hubble tension in like, okay, this is a problem, but like we don't know how to resolve this, but there's no mention at all of like any of the other problems, frankly. And so luckily I've been exposed to, I've had the fortunate, let's say, I was fortunate to meet Pavel early on in my studies. So I did have a good grasp of this, like of these, knowing of these problems beforehand, but it was very interesting for me to see that old and seasoned professor, so that was Peter Schneider, frankly didn't even bring any of that up.
Yeah.
I think, Sergey, do you remember? I think it was mentioned once about the like old galaxies, and he said like, of course, it's not a problem. None of this is a problem for Lambda-Cerium. He said this during the lectures that you're fools basically to believe that this causes Lambda-Cerium problems. Like it's not a contradiction. So it's just that the view is that this is not an evidence against the model with JWST. So.
So, Stacy, did anyone write a response to your AppJ paper on JWST?
Hello, am I back? I just missed like 5 minutes because my
And that's yeah.
screen was frozen. So you can hear me now?
Yes.
We can hear you
Okay,
fine.
good. So this recent AppJ paper on JWST?
Yeah, is there a reply? And did anyone disagree with you in writing?
No. The only things I've heard are secondhand, comments. Most of which were things we did talk about in the paper. Oh, it can just be a different IMF or something like that. And, we address that possibility and it's hard to completely exclude, but it's not going to explain the kinematics, for example, in that case. The only thing that I've heard that we didn't already address was a complaint that we didn't do simulations with star formation in molecular gas, which is a bit of a red herring because big cosmological simulations don't do that either. If you do a big box cosmological simulation, then you don't actually resolve star formation, and all that happens in what they call subgrid physics, and they use an analytic approximation that's informed by data, which is pretty much what I did. So I think it's mostly just been ignored. which has been my experience with some of these things. You know, I often wonder how many predictions a theory has to get right before it's admitted to be a theory, you know.
So can I ask this somewhat provocative question? Is the resistance to MON more in the US than in Europe?
I could actually say a lot about that on a country by country basis. There's something about national character there. But yes, there's a lot of resistance to it in the US, and that's not true everywhere in Europe, just some parts of Europe. I think Pavel has some thoughts on that.
Pavel, you want to say
Well,
something?
yes, sure. I think Europe is, as usually seems to be the case, advanced there. We have definitely a much richer research landscape here for reasons which one can ask why that should be the case. But in Italy, in France, there are indeed groups who are much more Mond liking than any place in the United States or Canada, apart from Stacy's pioneering, holding up the flag there. For example, here in Bonn, I'm actually including Mond into my lectures, like significantly. I'm very clearly communicating to students that dark matter is just nowadays rubbish. It was an excellent hypothesis, scientific hypothesis. Meanwhile, it's rubbish because it's been ruled out. So there's no point in discussing it further. That's what I've communicated in a few minutes ago. We actually have a full lecture course on Mond now here by Jan Flam Altenburg, who's lecturing the theoretical background and solving the equations of motion, two-body, three-body problem, and in really great mathematical detail. And that's been accepted despite some opposition, but it's a part of the curriculum here in Bonn. So for some reason, we are definitely much more able to do this in Europe than elsewhere, and I'm not quite sure why that is the case. I think potentially one reason is that the concept of science being a competitive endeavor, which seems to me, at least that's my interpretation from America. So the capitalist type approach, the best idea wins, doesn't work in science because you can't compete like that for fundamental ideas. Yeah, they either come or they don't come, but you can't have two scientists competing for some sort of fundamental idea and getting rewarded by grants. It just doesn't work, and that's not how it worked historically. You need freedom to do research, and that freedom seems to be more guaranteed. It's not perfect, but it's more guaranteed here in Europe in the sense of not being so dependent on grant money. While in the United States, I think one is much more dependent on grant money in terms of one's existence at the university.
Yeah, that's what I found. I should mention an analogous situation in quantum foundations. Now, if you say that quantum theory needs to be modified to explain some of its foundational problems, it's easier to work on that, I found in Europe, much easier as compared to the US. In the US, this idea is just as Stacy's sort of almost solo on MON in US, there's Stephen Adler at Princeton when it comes to modifying quantum mechanics. It's very difficult to. So I don't know where this comes from, but yeah. But I noticed that as APJ, the Astrophysical Journal, regularly publishes MON papers, whereas Physical Review D may have some resistance, I think.
Yeah, I mean, that's varied over time, and we can get into the details of how that works. But on that specific example, there's a long history in astronomy of being wrong. And so that's not something that's culturally shared by the physicists that, you know, and I was a grad student in both physics and astronomy here, and this is something where the teaching of the subject's very different. There are a lot of well-established results in physics, and so it's easy and in fact hard not to present the history of the field as a relentless progress and series of successes with really precise experiments. And so that develops a mindset in the student that, you know, we know all these things and it's not reasonable to question them. Whereas in astronomy, we have the experience of being wrong all the darn time. And so that propagates up into the journals of being a lot more tolerant of, papers that seem, oh, this just can't be right, but oh, maybe it is, because it turns out that way. And so I still see that sociology. So when I switched from physics to astronomy, I brought with me an attitude that is imbued in a lot of physics students, certainly in the US, that, oh, this astronomy stuff is trivial. I'll pick it up like that. And I see that all the time. But my experience was after a couple of years in grad school in astronomy, I had this epiphany that, oh, there's really good reasons, historical and sociological as well as scientific, why astronomy and astrophysics is a separate field from physics, and especially particle physics. And that was part of my experience, right? It's part of my education. Most physicists don't get that side of the thing, and I see exactly the attitude all the time. Oh, just some crazy astronomer talking about this stuff. And so it's really hard just to get past that initial attitude and start talking about the actual science.
So, Jinder, I do apologize for coming in, but Bernd has been wanting to make a point for quite some time.
No, sorry, Bernd. I'm sorry I missed you. Go ahead, please.
I promise it will be brief. I have a question for Professor McGaugh. Will you write more about the possible link between Mond and Mach's principle? Or...
I don't have anything to add to that.
Okay.
I think it's an intriguing idea. There's not a lot written about it out there, but none of it is by me, and I don't really feel qualified to add to it.
I at least remember one name, Bernd. You can look up my Indian colleague, Santanu Das, I think, from Bangalore. He has some interesting work on a Machian modification of general relativity and is hearing on Mond. I could send you a reference.
Yeah, that would be great. That would be
Paper
really
some
great.
time back, yeah.
And then I have...
there's also another paper by Manuel Lorena Paloma on Mach's principle and Mond. And I think because I was talking to him, he might give a talk in one of the seminars.
Okay.
So I can just send you a link when
yeah, that would be great.
So yeah, it's basically Mond as a transformation between non-inertial reference frames via Sharma's interpretations of Mach principle. So
yeah,
could you send that to me as well, please?
Yes.
Anastasia.
I'll just
I'm especially interested in anything which connects with the Machian perspective.
I think it's very interesting. Yeah.
My picture of Mond is what happens to de Sitter geometry if you add a little bit of matter to it. If you add too much matter, it becomes Newtonian gravity and GR. If you add little matter, you get Mond. And if no matter, then you get de Sitter. Mond is a mediator between de Sitter and general relativity.
May I add something to this? And I have to admit that my next question will probably be rather dumb, but I apologize in advance. But some of the relativistic versions of Mond do add additional fields to the gravitational fields, and some of them also have mass. I know that this is not dark matter in the original sense, but might additional massive gravitational fields also have the same trouble with dynamical friction traditional dark matter might have? And could this be used to exclude such theories? Or is the situation different because the additional fields are part of the gravitational part of the Lagrangian and not of the matter part? That's the question I have.
My impression is that it really depends on the implementation. So it is certainly a valid concern. In the implementations I've seen, it doesn't become a big thing. But that's related to the issue that TB has found in testing the ether scalar tensor theory, that there were regimes in which it worked and it didn't, and to get it to work everywhere at once with, you could have exactly that kind of problem.
Okay, thank you. And thank you for the link.
I think the last time Moti answered that, Bernd, by us differentiating between Mond and particle dark matter. Do you need a new force, say something like a fifth force, or do you stick to four forces and just say a new massive particle acting as dark matter because of the gravity of its weight.
I see, but I need to be careful not to repeat myself. Imagine you have an additional force carrier, but it's massive, like the vector bosons in the weak interactions.
But it would be like saying that in nature there are 5 forces, not 4. Whereas if I
Okay,
put
but
dark matter particle, I wouldn't say there are 5 forces.
but the force massive, maybe we don't need a massive force carrier, and then my question is completely meaningless. But in some, for example, there are some scalar tensor series where the scalar field is massive. So, and where you also have some, if you quantize it, which might be very difficult, you also get particle excitation. So you get massive scalar ones. I think they're called scalar ones or scalons. And could the scalar ones also clump and form the clouds, which might you get into trouble with dynamical friction? This would be my question. If you add some kind of massive particle, also only to the gravitational Lagrangian, might this also get you into trouble with dynamical friction, or is this confined to adding a new massive particle and not changing anything about the forces? This is something which interests me.
I have a question related to that. I don't know, there are probably people more knowledgeable than myself on this point, but my sort of zero order feeling would be that since gravitational waves travel at the speed of light, any force carrier would be massless. Would that be a valid argument?
I think at least MON is a long-range force, so its force carrier I would expect to be either
Massless.
massless or extremely low mass, so that the associated wavelength is on galactic and cosmological.
Okay, this would, I think, maybe solve my question. It's really a question, I don't know, so that's why I'm asking the question.
Sure.
Yeah, I mean, I can think of examples. So, for example, like the superfluid theory of Curie, there is this very low mass particle that endows Mond-like particles within a region where you essentially have a Bose-Einstein condensate at small radii, and that gives Mond-like behavior in galaxies, and then it's more ordinary dark matter-like beyond that. That doesn't really add any friction by the way
Okay.
it's constructed, because those wavelengths are very long.
Okay, thank you. Thank you very much. I think that answers my question.
Michael, should we wind up now?
Well, it's been an utterly fascinating discussion, but we have been going now for well over 2.5 hours. So unless anybody else has got a point they want to raise, I think probably yes, we should perhaps draw it to a close. But thank Stacy for a very rich and very fascinating exposition. Certainly has shifted the dial on Mond for me. I learned a very great deal. I'm sorry, Anastasia, you wanted to come in, please.
No, I just want to say thank you, Stacy.
Okay. I don't. If there's anybody else who wants to make has a further question, don't let me stop them. Okay. But I just want to say sorry.
I would just like to thank Stacy for keeping pushing this. I mean, it's personally, I think his work was instrumental to see the light.
Yes. Yes, you've had a lonely furrow to plough. I've seen. I'm just commenting on the sociology. I salute your intellectual courage and principle. It's been a fascinating experience. Thanks to everybody for a very, very rich discussion. I think this was one of the most intense and rich discussions we've had in the whole history of OSMU, which I think is saying quite something. And yes, thank you to everybody. And can I just say very quickly, I think perhaps one of the reasons that more attention has not been focused on Mond, given what I think are its very compelling phenomenological claims, is the absence of, well, the perceived absence of any fundamental theoretical underpinning for the theory. And that is something which does present a challenge. And it's one of the things, I'm just using this as an advertising space. In a month's time, we have Igor Konachikov talking precisely on that, on his proposals for fundamental theoretical derivation for the mass gap in Malziel and for the acceleration parameter in Mond, and for the cosmological constant from his pre-canonical quantization proposal. So anybody's interested in hearing that, I urge you to come along. That will be in 1 month's time. And then in 2 weeks, in between that talk by Igor Konachikov on the 21st of March, and on the 7th of March, we have Latham Boyle, who is going to be talking on, sorry, Tajinder, can you just remind me of his title?
His work with Neil Turok on the two-sheeted universe as an alternative to inflation. It's a very interesting work.
Very interesting.
To add to what you said, Michael, today by Luc Blanchet, there's a paper on Archive GRQC on a SU2 Young-Mills theory for Mond. And I myself have a U1 gauge theory for Mond.
Very interesting.
We have 3 candidates now.
We have 3 candidates. Of course, one of the things about Igor's approach is that he actually has a derivation for the Yang-Mills mass gap in his theory, which is also very interesting. So, okay, so Latham Boyle, very interesting talk to come, though not directly connected with Mond. And then, as I say, in a month's time, we will have another talk which is very much directly connected with Mond, which, as I say, is Igor's talk about the theoretical derivation of Mond from his pre-canonical program. So, unless anybody has anything to add,
later this year, Pavel will talk about the tidal tales of open.
There will be plenty more. There will be several more Mond-centered, Mond-connected talks in the program for this year. I was just mentioning the next 2.
Sorry, can I ask, do we have a program yet for the year?
Yes, we do.
I'm not sure I've seen it.
I'll mail it to you, Anthony.
Okay.
I'll do that.
Yes, thanks. So it has only recently been revised. So I think you literally got out the latest revision only a couple of days ago, didn't you, Tajinder?
Yeah. I think Xavier is saying something.
Yes, if I could add just a final whimsical note. Yes, for a very long time, 40 years perhaps, the one of the main missing ingredients was, wow, we would really like to have a fundamental theory, a fundamental general relativistic extension of Mond, whatever. Over the past couple of years, I think we have too many.
Yes. But that's a good thing, no?
Yes. Well, it's like the number 9 bus. We always used to have the joke. You know, you wait for hours and hours, and then 6 of them come along at the same time.
If we can have so many dark matter candidates, we should also have many relativistic Mond candidates. Yeah.
Anyway,
One that
more
works
and more
in the
people are
end.
sitting up and taking serious notice of Mond. That's
Sorry, what, Indrani? You said something?
No, I said we should have at least one which really works in the end. Having too many candidates that also don't work is also not good.
No, but this at least it's an indicator that
of course,
there is a shift towards the theory of Mond. Yes.
Of course. I just
well, the jury is out as to whether they work or not. Of course, these are very early days, but yeah, to take your point. Anyway, well, once again, very, very big thanks indeed to Stacy for a marvelous talk, and to everybody for a very good discussion.
Yeah.
We'll see you on the 7th of March with Latham Boyle. And thanks to everybody.
Thanks,
And a big
Stacy.
shout out and thanks to Roger for having
Bye-bye.
come. He's left us, I know, but I was very glad to see him here.
I'm logging out. Bye-bye.
Okay, bye.
Cheerio, Tajinder.